Okay, welcome back. So we continue our discussion on the BEM theory, which is blade element theory. And so if you recall that what we have been talking in the last session is that we got that velocity triangle where we had the effective wind magnitude based on the relative axial wind speed, and which is also partly you can see this is your resultant effective wind, and your axial wind would be in this direction, which is your axial wind. That would be u infinity a into 1 minus a. Okay, and then you have uh, sorry, you would be into 1 minus a, and uh, this direction is induced tangential wind, which is nothing but r omega 1 plus a prime. So, and then you could find the effective wind thing. Now, what you can here, what we are trying to find out the lift and drag on the blade element. Okay. So that's what you are trying to find out the lift and drag on the blade element. Now, what we can write DL, DL is the lift component on this blade element, which is shown again. Your flow angle phi is alpha plus beta. One is the angle of attack, and this is your chord line. So what you get, the DL is half rho W square DAB into CL. And similarly, so what you could do, okay, so probably this was 26. So DL is, and then DD, which is drag half of rho W square DAB into CD. So these are two things. Now here what you have sine phi, which is u infinity 1 minus a by W. You have cos phi, which is r omega 1 plus a prime by W. Then what we have, axial flow on all blade elements, that is d of Fa, okay, which is equals to b into dl cos phi plus dd sin phi, okay, and we can have tangential force on all blade elements, that would be dAp b into dl sin phi minus dd cos phi, which is 28. So this would be positive if the blade element produce power. Okay. So now what we can do is that, so these are what you have. I mean, in some text you can find this axial axial force. The axial force is equivalent to term normal force. So some textbook can write this dFn, but obviously tangential wall would remain as a tangential. But then also one can find out using DFT, one can find the differential torque due to this FT, which is dq br dft. So this is also one can write down. Now, what here we have axial and tangential force cause induction A and A prime due to momentum balance as before. Okay, so that is there. So now what we have, now we have axial force dFA, which is dm dot 2a u infinity, which is 29a, which is rho 2 pi r dr u infinity 1 minus a. So that gives dFA half rho u infinity square 2 pi r dr 4a 1 minus a, which is there. So that's what the axial force that you get. So this elemental ring would give you an idea if the wind coming through. So this very clearly shows when the wind passes through, this is rotating, which way the axial force would act and which way the tangential force would act. And this segments one can think about, this is where you have those blades. So now what you can have tangential momentum change. So that is dft dm dot a prime r omega, which is half rho u infinity r omega 2 pi r dr 1 minus a 4a prime. So now from 27 equation equals to equation 30 and equation 28 equals to equation 31. So we get two equations for two unknowns a and a prime, which need to be solved numerically. So then you can find out. Then you can find out essentially from here a and a prime can be found out. Okay, so that's how you get that you have these equations. Then you get. So let us now let us first correct and simplify our equations to find out that thing. Okay, so let us kind of try to do that. So again, we get back to this particular picture so that I try to make things more visible in a fashion that you can follow. So now first we will write equation 27 equals to equation 30. So what it is there, half rho W square B C into CL cos phi plus CD sin phi into dr equals to half rho 2 pi r dr u infinity square 4a 1 minus a. So this is 32a. So from here what we get, W square into B C into CL cos phi CD sin phi 2 pi r infinity square 1 minus a. Now similarly we have equation 28 equals to equation 31. Then you have half rho W square BC CL sin phi minus CD cos phi dr half rho 2 pi r dr u infinity r for a prime 1 minus a, which is 33a. That gives W square B C CL sin phi minus CD cos phi 2 pi r square u infinity omega 4a 1 minus a. So this is what we have now. Okay. Now we can use the concept of solidity. So we use solidity. Sigma r is br by 2 pi r, and our local speed ratio lambda r is r omega by u infinity, and w is u infinity square lambda r square 1 plus a prime square u infinity square 1 minus a square. So this you will have u infinity lambda r square 1 plus a prime square plus 1 minus a square. So let's say 34a, 34b. So what we have, this is our triangle that we have. So this is W, this is P, so this is cos, this is sine. So what we have, sine phi 1 minus a root over lambda r square 1 plus 1 minus a square, and cos phi lambda r 1 plus a prime lambda r square 1 plus a prime square plus 1 minus a square. So that's what is happening. Okay. So what we therefore we get the equivalent formula from equation 32b. What we get that lambda r 1 plus a prime square plus 1 minus a into sigma r cl. So what? So cl into basically what we have lambda r 1 plus a prime root over of lambda r square 1 plus square plus 1 minus a square cd into 1 minus a lambda r square 1 plus a prime square plus 1 minus a square equals to 4a into 1 minus a. So if we so that we can write lambda r 1 plus a prime square. So what we get plus 1 minus a square sigma r cl lambda r 1 plus a prime cd 1 minus a equals to 4a into 1 minus a. So 32b. So this is what we have used. So w square. So this is supposed to be lambda square. So and this is supposed to be okay lambda square plus so 32 we get here b. Okay, okay. So this is essentially w square. So this has to be square. Perfectly fine. Now, similarly, from equation 33b, we get lambda r square plus 1 prime square 1 minus square by lambda r sigma r cl 1 minus a minus cd 1 plus a prime equals to 4a prime minus 1 minus a. So this is essentially from that. Now, what happens if we kind of now dividing both 35b and 35b by equation 36 for each side we have lambda r cl lambda r 1 plus a prime cd 1 minus a cl 1 minus a cd lambda r 1 plus a prime a by a prime. So we get this. So what you have is that so now if you recall from the rotor disk theory, A prime equals to A into 1 minus A by lambda r square. So what we have, A prime equals to A by lambda r, 1 by A minus CD by CL lambda r 1 plus A prime divided by lambda r 1 plus A prime CD by CL 1 minus A. So it's more like a little bit of algebra of doing that. So we can write A 1 minus A by lambda r square 1 minus CD by CL lambda r 1 plus A prime by 1 minus A 1 plus CD by CL 1 minus A 1 by lambda r. So 38B. And if we get the quadratic equation in A prime, so we get A prime square 1 plus CD by CL into 1 by lambda r A prime minus A into 1 minus A by lambda r square minus A by lambda r. So here only one only positive solution is meaningful. So what we get, A prime equals to minus 1 plus CD by CL 1 by lambda r by 2 plus minus, so it would be only plus 1 plus CD by CL into 1 by lambda r square by 4 A into 1 minus A by lambda r square minus CD by CL A by lambda r. So this is what. So that's what we get. And for a special case, let's say for CD equals to 0, we set A prime equals to half plus minus half plus 1 by 4 plus A into 1 minus A by lambda r square, which is 41A. So we can write minus half plus half 1 plus 4A 1 minus A by lambda r square, 41B, which is minus half plus 1 by 4A into 1 minus A by lambda r square. So this is, we can write A into 1 minus A by lambda r square plus 4, which is 41D. So this line that we are writing by using Taylor series expansion root over 1 plus x, which is 1 plus x by 2 plus order of x square and so on. So this is the higher order term that we have left it blank. So this is what you get. Okay, that if the drag is 0, then you get A prime, which is the radial induction factor, kind of. So essentially, no drag condition, your A prime is A into 1 minus A by lambda r square. So that's the relationship. But no drag condition is more like an very much a theoretical condition, because whenever these turbine blades are exposed to this rotation and the wind speed and uh, such things, then it is very, very difficult to uh, have zero drag condition. So what we have, rather, when these are uh, exposed to that rotation, then this lift flows on the rotor blade. It causes the blade to rotate, and there will be some drag, and there could be delay in the, I mean the loss in the drag, and then this drag can affect the power output. So that is what your overall power output, having those efficiencies which are considered to be, mm, because whatever available wind power is there, you may not be able to um, extract that completely through that. So this is what we what we have talked about is that we have actuated this theory, that is a momentum theory. So we talked about actuated this theory, and then we have talked about blade element theory. So these are, both of them are kind of momentum theory. But when you talked about actuated this theory, we have not considered the rotation of the weight, which is there, and because of that, you may start getting some performance effect. And in the wake rotation, we consider the rotation of the wake into the system, and that's what we talked about the BEM theory, where you consider on all these things. So we'll look at some of these details further and continue the discussion in the next session. Thank you.